Hi, thank you for choosing to watch our video as a part of Rappaport's STEM Night. All of the experiments performed in this video depict chemical and physical changes which happen every day. Some of these changes apply to manufacturing, and others are just for fun. Enjoy.
For our first physical change, we use the X carve, and as you can see here in the video, we have an X carve with a 1/8 upcut drill bit, causing a physical change to MDF wood. It's a DeWalt 611 router on the X carve, which is spinning at a rate between 16 and 27,000 RPMs, revolutions per minute. And it's slowly cutting each layer of wood, turning it into a fine dust. For our second physical change, we decided to cut styrofoam. We had got a big piece of styrofoam with two thicknesses. The first thickness measured 340 millimeters, while the thinner side measured 240 millimeters. We turned on the thermal cutter and put it on level 6. Waited till it heat up. It took about 3-ish minutes. And then we slowly pushed the styrofoam through the cutting wire. There are also different levels for different thicknesses. And it makes the styrofoam melt when exposed to air. It hardens back to its original state.
The first chemical change in this video involves mixing two ingredients to create epoxy resin. The epoxy's composition is a homogeneous B-step solution, and it is synthesized with epoxy resin, solution A, and epoxy hardener, solution B. These two ingredients are mixed together through a solution polymerization process. During polymerization, smaller molecules called monomers are chemically combined to create larger molecules. A 1-to-1 ratio of both resin and hardener is necessary for the epoxy to solidify. If the incorrect ratio is used, then the integrity of the resin will fail, and a poorly structured product will be the outcome. If the epoxy resin composition is stable, it can serve as a self-bonding paint and coating and can be stored up to 12 months at room temperature. When mixing both the resin and hardener to create the epoxy, the creator has to stir both ingredients for 3 to 5 minutes. If the ingredients are mixed too quickly, the excessive heat builds upon itself and the mixture can heat quicker than expected, making the resin harden before it can even be poured into a mold or added as a coat. The heat formed from the two solutions is an indicator that polymerization, a chemical reaction, is taking place. Polymerization, as mentioned before, is the process of bonding monomer molecules together to form polymer chains, which leads to curing. As the epoxy cures, it passes from a liquid to a gel state before it reaches a solid state. What's interesting about epoxy is that water cannot clean it or remove it if you accidentally get it on your hands. This is because once it is mixed and in the curing process, it becomes insoluble. Since epoxy resin is a sealing agent, it can protect any surface from water, essentially making it waterproof, and that's one of the reasons why it's so valuable and highly used today. Due to its water resistance, only alcohol and acetone, and possibly a few other acidic substances, can dissolve or help break down epoxy. The reason that epoxy takes so long to dry is due to the temperature at which it has to dry. The general temperature range that the epoxy should dry in is 80 to 75 degrees Fahrenheit. So the cooler the room is, the longer the epoxy will take to dry. Additionally, the epoxy needs a longer time to dry to reach its full strength and durability. At most, it might take up to a week or even 2 weeks. But usually, it only takes 3 days, or maybe even 1 day in best case scenario. But for the example we did in this video, it only took a day.
For our chemical change 2, we decided to use a wood finish stain to stain the little design we carved using X-Carve. If we go in depth with the chemical change, we can see that the oil-based stain falls under the polyurethane reactive group. In this group, the stain is cured by a chemical reaction called the enzymic oxidation reaction, in which the enzyme or the stainer comes in contact with an oxidation agent, which in this case is oxygen. This forms a new chemical that darkens the color of the wood.
The final chemical change in this video is the creation of a lava lamp with cooking oil, vinegar, food coloring, and baking soda. As the experiment was carried out, drops of blue-colored vinegar were sprayed into a glass cylinder with cooking oil and baking soda at the bottom. The vinegar is more dense than the cooking oil and therefore sinks. It reacts with the baking soda, causing bubbles of carbon dioxide to form and rise to the top of the cooking oil. The vinegar dissolves the baking soda, causing it to sink back down and react with the baking soda again. This process happens continuously until none of the baking soda remains, and the formation of carbon dioxide gas proves that a chemical change is taking place. This experiment was the most entertaining, so you'll see how everything played out.
So it's just releasing oxygen, but as we drop the vinegar, it's going to sink to the bottom, and then it's going to react.
I'm pretty sure I'm right, because I did this before. But if I'm not, oh well.
Throw it all in there.
It's all, we just want to get the baking soda dissolved. That's crazy, bro. It just keeps like, oh.
Where's the lid? Put the lid on.
You're rubbing it very suspiciously.
Watch out.
Oh, you should,
What if I like?
you just want to pour the whole thing in there?
Can I just like
You just want to start pouring it in here?
The baking soda?
do it? Do it actually.
It's not all gone yet. Just start pouring it.
This?
Yes.
Do it.
Drop. Okay.
3.
Just enough. Just like a little bit.
How do you always overdo things?
It spreads out a lot. I'm sorry, I can't even keep the video straight. That's
You got good angle?
yes, I do. We call a chug splash.
You ready? You ready? You ready? Yeah. You ready? You ready?
Is it going to do something? Oh no. Oh, big reveal, guys. It didn't explode.
If we had left the lid on the makeshift lava lamp for a longer period of time, there would have been an explosion because the amount of carbon dioxide gas trapped within the container would have broken it open.
No, it's a good. I think it's good.
Right there.
Yes. Yeah, that's.
It better be enough.
I'm just gonna get a close up of the.
I'm telling you, just throw your camera in there at this point.